Today's video. I want to thank y'all once again for watching my videos. It means a lot to me. But to get started for today, we're going to be talking about more types of functions. Calculus is really based on having a strong foundation of functions, and it's useful to actually understand how we can derive or make new functions. I'm pretty sure most of us have learned of several parent functions, such as y is equal to x squared, or e to the power of x, or just things like that, or the square root of x, x cubed. We all really have this basic idea of what those graphs should look like. But where it might start getting foggy, or even you might not know, is if there is something that has transformed that graph. So, the first thing I'd like to start out with is, what happens to a graph if we add a constant c to it? Well, a positive constant c. Well, it's going to move that graph upward. So it's going to shift that graph upward. And I'm going to draw an arrow just so you can more or less visualize it. Looking at f of x minus c, on the other hand, that's going to shift the graph downward by a distance c. So it's going to go downward. And I'm just going to draw a downwards arrow. Well, what happens if we have the c on the inside? Well, if we have a plus c on the inside, it's going to shift the graph to the left by a distance c. So it's going to shift left by a distance c. And the opposite happens if we subtract. It's going to shift right a distance c. So c here is just a positive constant. Unless you're subtracting it, then in that case it's adding a negative constant, but I digress. So what this gives us the power to do is now move around the original function. Well, we know a parabola is y is equal to x squared. Let's work on this problem. So find an equation of a parabola that is shifted left 3 and up 1. Well, I'm going to define this as f of x. And we know that f of x, well, according to our rules, so it's going to be shifted left 3. So it's going to add 3 on the inside of it. And now we want to also shift it up 1, so it's going to be plus 1. So this is kind of hard for us just to plug into our original equation. But if f of x is just equal to x squared, we can say that x plus 3 squared, because that's our f of x, and we're just subbing in x plus 3 for our x, plus 1 is our equation, and if we want to expand that out, we'd get an equation for our line that would look like y is equal to x squared plus 6x plus 9 plus 1. So our final equation for a parabola that has been shifted left 3 and up 1 is going to be x squared plus 6x plus 10. And we can also go backwards from this too. For example, if I wanted to know like where this graph has been shifted from, let's say that I have a parabola, and this really works for any equation. I'm using a parabola just because it's an easy parent function to work with. Let's say we start with y, or let's once again define this as f of x is equal to x squared plus 10x plus 31. Well, we can complete the square, so we would get x plus half of this is going to be 5, and we're going to square that. And then, because that should be a plus 5. Since we were getting another 25 out of nowhere, we're going to subtract that off. So this should just be f of x is equal to x plus 5 squared plus 6. So this would be shifted left by 5 units, left 5 units, and up 6 units. So that's kind of how you can go from an equation to knowing how far shifted left to right it is. Moving on, today's video should be a lot shorter than yesterday's. We have vertical stretches and vertical and horizontal stretching and reflection. So f of x plus c is going to stretch the graph f of x by a vertical factor of c. So what that's really going to look like is how do I want to explain this? It's like you're pulling it, like, it's kind of hard to explain, but we're just going to write down is going to stretch the graph f of x. F of x by c. Alright, now I want to suppose that c is actually going to be greater than 0 for all of these. That way this works for all of them. Now if it's a reciprocal of c that we're multiplying by, or it's f of x over c, rather, it's going to shrink the graph. The graph f of x by c. So if you're thinking of a parabola again, the point 1, 1 is on the parent function of a parabola. But if I say c is equal to 2, then that c, or that point 1, 1 is now going to become the point 1, 1/2. It's going to shrink it. It's going to make it smaller. If we are multiplying, all of these are in the horizontal direction, by the way. Horizontal, and horizontal. Horizontal. There we go. And then if we say that f of x, or f of c times x, rather than c times f of x, that's going to do something different. In fact, it's going to shrink the graph. Shrink the graph f of x by a factor of c in the these are vertical. I don't know why I said horizontal. These are vertical stretches. Vertical. And this is a horizontal. We'll shrink the graph f of x by c in the horizontal. If you have f of x over c, it will stretch the graph in the horizontal direction. So I'm going to just write this down as stretch horizontal. Now, these two things here, let me make this bottom one just a small bit clearer. So this is saying negative x. And what this top one's going to do is this is going to reflect over the x-axis. So if you take your parabola and it's sitting right here on the x-axis, it's now going to look like an upside down U. Now, if you reflect, now this f of negative x is going to reflect over the y-axis. So I'm going to use a different graph this time because the parabola will look the same. So let's say that we have a logarithm. So I'm going to plot 1 point away from the unit, and that's going to look something like that. Well, this is f of x, and in a different color now I'm going to do f of negative x. Well, we got that point. It's going to go up, it's going to go out and over, and this is going to be f of negative x. Alright. Now that we got these definitions done with, let's try a problem. So I want us to try to graph f of x plus 3 or if f of x is equal to x squared plus 3 and g of x is equal to negative 2 f of x minus 3, plot g of x on a graph. Well, this is actually not too difficult to do. Well, I want to start by plotting this parent function here. Not really a parent function, but it's going to be the original function. So x squared plus 3 is going to have points roughly about here on the graph, over 2 and up 4. So that should be 7, and negative 2 should also be 7. And this is our general graph of our parabola. Well, g of x has done something different. I want to start by, first things first, finding where it's moved to. So in this case, it's going to move right 4 units. So let's plot this. So it's going to go over 1 unit, 2 units, 3 units, 4 units, down 3 units. So this right here is going to be our starting point. I'll erase that. And we know that it also is going to be flipped over the... No, I don't want to erase. No thank you to erasing. Undo that as well. But we know because of this reflection, it's going to be an upside down parabola. But it also has a stretch. So we're going to go over 1 and down 2. Over 1 and down 2. And then it would go over 1 down 8, but I don't have that many points marked. So this right here would be our parabola, or our function g of x, if this is our function f of x. Continuing on, we have a very unique topic. Composite functions. Composite functions are very unique. And I say that because this is the part where functions might be able to get domain restrictions, even if they didn't have them before. So let's suppose that let's ask first, what is a composite function? Well, it's a function that is composed of another function. So this is really just going to look like f of g of x, which is also the same thing as f of g of x. Now, what this is really saying is, let's suppose we have an input x, and we're going to first input that x into g of x. Then that g of x's output is going to be input as the input for f of x. And then whatever we get is going to be our output y. And that's the entire idea of composite functions. So let's let's try breaking down some functions into their composite forms. So let's suppose that we have a function a of x is equal to the square root of x cubed minus 4. Well, there's a lot of different ways we can break down this function. In fact, let's list a few pairs. So, for one, we can have b of x is equal, and let's just say, for simplicity's sake, that a of x is going to be equal to b of c of x. So, our b of x, in one case, could be equal to just being the square root of x minus 4, and our c of x could be x cubed, as this is going to go into the input x, and that would make it our original function a. Undo that. Okay, another possible choice that we could do is b of x is equal to just the square root of x, and c of x is equal to the cube root minus 4. Another way that we could break this down is b of x is really just equal to there's a let's see. I think this is going to be some of the more easier ways to break this down. But there is going to be one more way that I'm going to suppose. B of x could be the fourth root of x. And c of x could be equal to x cubed minus 4 squared. There is 1,000 different ways that you could break this down. And that really shows you the compositry of the function. Even a function as simple as f of x is equal to x squared can be broken down. But in all honesty, that's going to be a very simple function to break down. Or at least you'd think it would be. Just for one more example of this a of x, we could do b of x is equal to e to the x, and c of x can be the natural logarithm of the cube root of x cubed minus 4. Plugging that in, you would get the same result. You can get more and more crazy with these composites. But I wanted to just start by working out a few composite functions and deriving some formulas here. How can we formulate a composite function? So let's start with A here, and we're going to work all of these in white. I'm trying to use more colors than just pink. So h of x, which is going to be this one, is equal to the square root of x minus 1. F of x is ln of x to the power of 4, and g of x is x squared minus 4. So A is going to look like, well, we have a square root is equal to. Now, what is g? Because g is going to be going in the place of this x here. So that's going to be x squared plus 4 squared minus 1. If you really wanted to break this out, you can, but I wouldn't recommend it. What about f of g of x? So we would get the natural logarithm of, let's see, that would be x squared plus 4, and this here would be to the power of 4. Look, going onward to C, we have g of h of x. So this would really be equal to, well, our g is x squared plus 4, and we're putting this in as our square root. So this is just going to be the square root of x squared minus 1. Square that plus 4. And this actually can be simplified. We're going to cancel the root. So we'd get x squared plus 3. Now, I've switched back to our original notation that I used, like g of f of x. And that would be the natural logarithm squared of x to the 4th plus 4. Very strange looking, isn't that? But it is technically proper math notation. Now, we can also use the same function for our composite as our original function. So we can have like h of x or g of x. So in the case of h of x, we are going to plug in the original h of x. So that would be the square root of x squared minus 1 squared minus 1. And this actually does simplify down to be h of x is equal to, well, the square and the root will cancel. So we are going to get the square root of x squared minus 2. And now let's do the same thing for g of x. So that is going to be x squared plus 4 squared plus 4. Now, if you want to expand that out, you can. It would be x to the power of 4 plus 8x squared plus 16 plus 4. And that would give you x to the 4th plus 8x squared plus 20 for a composite. And you'll notice that sometimes the composite functions look nothing like they should be a composite function, especially if you expand them out. But they truly can be, and are. Now, a very interesting thing about these composite functions is they often, or these combinations of functions, have domain restrictions. And you'll understand why this is important. I'm going to ask this question right now. Is the square root of x squared the same thing as the square root of x squared? And the answer to this question is it's not. On one hand, this left side is only going to be for positive numbers, or for x greater than or equal to 0. On the right hand over here, we're actually going to have the absolute value of x, which is all real numbers. That's kind of strange, isn't it? Because these can technically be represented as x over 2 to the power of 2 over 2. But they're not the same. The point I'm trying to get at is, in both these cases, one of these is going to be f of g of x. The other of which is g of f of x. These are not the same thing, even though they look almost identical. And the key differing factor is the domain of this inside function. You cannot get numbers that are going to be outside of the inside function's domain, even if the outside function, or the f or the g, is going to cancel it. It's not the same. So even if you have h of x is equal to the natural logarithm of x, and f of x is equal to e to the power of x, f of h of x domain is going to look like e to the ln of x. It's going to look exactly like x, but its domain, because this natural logarithm cannot take negative numbers as an input, is just going to be x greater than 0. Greater than or equal to 0. So let's try to find some domains of some of these functions, of some new composite functions here. And sometimes, even if an output works, and it is defined, the domain is defined, the range can sometimes make the outside function not defined. So let's define 3 new functions. H of x is equal to the square root of x squared plus 3. Or, yeah, you know what? Scratch that. It's just going to be x minus 3. We're going to have e of x is going to be equal to the natural logarithm of x. F of x is going to be equal to, let's say, negative x squared. And then let's just define one last function. G of x is going to be equal to cosine of x. Now, what's this going to look like? Well, let's start defining a new function and finding its domain. Well, h of x, well, let's do h of g of x. And I need to make my eraser smaller again. H of g of x. Well, let's start out by saying cosine of x minus 3. Well, does cosine of x, is it ever going to be undefined throughout its domain? No. For cosine's domain, its entire domain is real. But what about this square root part, the h of x part? Is this ever going to be equal to 0 or negative numbers? Well, cosine's range is going to only be from negative 1 to 1. So this poses an issue because the max value this radical will take upon itself is going to be negative 2. So for this function, it has no domain. So this composite function, no matter how you will work it, it will never have an output. Well, let's work another problem. What if we did the natural logarithm of cosine of x? Okay, so let's define a new function. E of, let's propose E of, let's call it g of x. Again. So, in this case, cosine of x is going to be negative from values of pi over 2 to 3 pi over 2. So this is actually relatively interesting, where the domain of e of x, or the natural log of cosine of x, is going to look something like pi over 2, let's call it negative pi over 2 to pi over 2, and these are going to be in open brackets, as the natural logarithm cannot be equal to 0, plus 2 pi n, which is like the strangest domain ever. But it's true. In this case, all of the outputs should have, or every input should have an output, other than for that of which cosine is negative. Defining another function, h of x is going to be equal to let's say h of x is going to be h of e of x. This is actually going to be relatively curious, almost. So, e to the x is going to have a domain of negative infinity, or not negative infinity, from 0 to positive infinity, not including either. So this is the domain of e of x. But h of x also has a domain restriction. It cannot be x minus 3 needs to always be greater than or equal to 0, so x has to be greater than or equal to 3. So this is going to propose an even greater challenge to find where the domain of this is going to start. So the way that we're going to do this is, so this is the square root of the natural log of x minus 3. Let's solve the natural log of x minus 3 for greater than or equal to 0. So we're going to say natural log of x is going to be equal to 3. So it has to be less than or equal to e or sorry, e to the power of 3 must be equal to x. So, the domain for this function is going to be e to the power of 3 through infinity, including them both. I believe. Yeah. Is e to the power of 3 as an input would give 3 for an output. Yeah, that would be correct. Kind of strange, isn't it? But this is what I have for you today for combinations of functions. I hope today's method of working through some more problems than what I normally do helped you understand the concept. I'm looking towards doing more problem solving in the future, but I hope you all found this video informative, and I hope you all have a wonderful rest of your day. Have a great rest of your day. Bye-bye.